Hello everyone, welcome back to my channel. Today we are going to analyze a research paper that is optimal scheduling of a smart home energy system, a user-friendly and adaptive home intelligent agent with a self-learning capability, which is based on the artificial intelligence. Abstract. Smart home intelligent agent, many objective optimal scheduling model, adaptive experiment study. This paper purposed a user-friendly and adaptive intelligent agent with a self-learning capability for optimal scheduling of a smart home energy systems. The intelligent agent autonomously identifies a model parameters based on a system operation data, eliminating the need of manual input and making it more user friendly and practical to implement. It can also self-learn the latest energy consumption information from an update dataset and adaptively adjust model parameters to accommodate challenging conditions. Utilizing these determined models such as an input, the intelligent agent perform a day ahead optimal scheduling using the purposed many objective integer nonlinear optimization model and the automatically control system operations. Experimental studies were conducted on a laboratory-based smart home energy system to verify the effectiveness of the development intelligent agent in a different scenarios. The results consistently demonstrated many absolute percentage error below 12.7% across all three scenarios, indicating the accuracy of the intelligent agent. Furthermore, the optimal scheduling significantly enhanced system performance after optimization, daily operational cost, peak level differences, and the CO2 emission were reduced by 3.1% to 81.6%, 29.2 to 36.7%, and 19.6 to 43.2% respectively. Moreover, the PV generation, self-consumption rate, and the self-sufficiency rate improved by 29.6 to 38% and 40 to 49% respectively. The purpose intelligent agent provides invaluable guidance for optimal dispatch of smart home energy systems in a real-world settings. Introduction. Renewable energy power generation technologies have been widely utilized in recent years, driven by the goal of carbon neutrality. As reported by the National Energy Administration, China's total installed capacity of a photovoltaic, that is PV power generation, reached 520 million kilowatt. As of October 2023, although the large-scale applications of PV generation reduced carbon emission, but the and also the intermittency and the fluctuations of PV generation pose a great challenge to establish stability of utility grids as the portion of PV generation increases. Leveraging the residential load flexibility can mitigate the impacts of PV generation on a utility grids. Associated with reducing the required capacity of the battery storages and enhancing system reliance. For example, changing the temperature set points of a thermostatically controlled loads, adjusting the operation time of a postponed loads can reshape household electricity consumption patterns and profiles to provide grid services for utility grids. To efficiently manage these flexible loads, the development of home energy management systems in imperatively. A HEMS can defined as a technology platform that enables to monitor, record, schedule, and control household flexible energy resources. Literature review is that the optimal scheduling of a smart home's energy system involves integrating advanced control strategies to manage energy consumption efficiently. Recent highlights the role of user-friendly and adaptive home intelligent agents in these systems, which utilize machine learning and optimization algorithms to balance energy usage, cost, and the comfort. Self-learning capabilities enable these agents to adapt to user behavior patterns, making energy decisions more personalized and effective. Techniques like reinforcement learning, deep learning, and a fuzzy logic have been explored for improving the agent's adaptability. Furthermore, smart agents can integrate with the renewable energy sources and storage systems to optimize both energy efficiency and the environmental impact. Research also emphasizes the need for user friendly interfaces, ensuring homeowners can easily interact with and control the system without technical expertise. Overall, this agent promised to make smart home more sustainable, cost effective, and responsive to dynamic energy demands. Methodology used is an optimal scheduling methodology for a smart home energy using a user-friendly and adaptive home intelligent agents can be outlined as follows. Objective: minimize energy cost while maximizing user comfort and efficient energy use. Energy forecasting: predict future energy consumption using machine learning models based on past data, weather forecast, and user preferences. Energy pricing: integrate real-time electricity price data, example time of use in traffics to optimize energy consumption. And third one is the user profiling, collecting user behavior data, example application usage patterns to create personalized schedules. Demand response: enable real-time adjustment in energy use based on user input and grid condition. Energy storage: optimize the use of energy storage, that is the batteries, to charge during off-peak hours and discharge during peak times. Renewable integration: incorporate renewable energy sources like solar or the wind, adjusting scheduling based on the availability. User interface: providing a simple and intuitive app or a voice assistant for a user to manage preferences, monitor users, and set energy saving goals. Adaptive control: use reinforcement learning to continuously adapt schedules to user habits and system performance. Device control: automatically control smart appliances, a lighting, heating, and a cooling system to agile with the optimal schedules. This methodology ensures the smart home energy system in efficient, adaptive, and the user friendly. Conclusion: a home intelligent agent was proposed for optimal scheduling of a smart home energy systems in a real world environment in this paper. Experimental studies were conducted on a laboratory based smart home energy system to validate the purposed intelligent agent in various scenarios. Additionally, a standardized development pathway for its practical energy engineering application was outlined. The main conclusion are drawn below. Those are the general gray model for distributed PV generation, thermo thermostatical controlled loads and postponed loads were developed based on these physical models. Model parameters of these purposed models can be identified using statistical analysis, multiple linear regeneration, and a K-means clustering method with a history operation data. Experiments result demonstrate the accuracy of these developed models. A user-friendly and adaptive home intelligent agent was proposed for optimal scheduling of a smart home energy systems. In adaptively, Appendix that identifies model parameter based on household operation data and can adaptively update these model parameters over time to accommodate changes in the condition. Experimental results proves the effectiveness of our developed intelligent agents with the maps between experiment and the stimulation below 12.7% across all three scenarios. Day ahead optimal scheduling significantly improves the performance of a smart home energy systems in terms of economy, environment, friendliness, and a PV generation consumption, except in a real world environment. After optimizing, peak loads were curtainized or shifted to a daytime periods coinciding with a PV generation or a low price periods, thereby enhancing system performance. Experiment results in a diverse scenarios reveals that optimal scheduling contributed to reduction that is 34.1 to 81% in a daily operation cost.